We can see the screen. We can see the screen if you.
It's right there.
The basic issue to be explained concerns an aspect of what is called associated production. Three facts characterize this phenomenon. New hadrons are produced in pairs. This process is observed. Not all pairs are observed to be produced in strong processes. That's number two. And the pairwise occurrence is broken in weak decays. A new quantum number, strangeness, was assumed to operate in strong interactions. Its values were chosen to be such that it is conserved in process one, but not conserved if process two were to be observed. The pairwise occurrence is broken in decays of the new hadrons. That's process three. The postulated values of strangeness were 0 for pions and nucleons, +1 for the K plus and sigmas, and -1 for the K minus. So the situation at the time strangeness was introduced was that strangeness was assumed to be conserved in strong processes by violated in decays. Parity was assumed to be conserved in all processes, and the domain of validity of assumed parity conservation is larger than that of strangeness conservation. A vastly new perspective on associated production was brought about by an unrelated discovery, that of parity violation in weak decays. This changed the situation drastically. Both parity and strangeness are violated in weak processes. The observed domains of validity of parity conservation and strangeness conservation are exactly the same. The quality of these two domains presents a puzzle within the framework of the presently accepted theory, because there is no reason why two such distinct phenomena, associated production and parity conservation, should have the same domains of validity. The currently accepted view focuses on associated production and does not address the equality of the domains of these two phenomena. My theory aims to explain this equality. In my opinion, these two domains presents as much of a puzzle within the presently accepted view as that presented by the numerical equality of inertial and gravitational mass within the Newtonian mechanics. As all of you know, that puzzle was resolved by the equivalence principle, according to which inertial and gravitational masses are numerically equal because they are physically identical. The principle provided the foundation for general relativity. What I have proposed is that the domains of validity of associated production and parity conservation are equal because they are physically identical. A single quantum number parity accounts for both phenomena. The theory built around this proposed physical identity specifies a set of observables that determine hadrons with the same electric charge and baryon number, and presently distinguished by different value of strangeness to be distinguished by different measurable values of double space inversion. The specified set of observables comprises the subset of processes that are allowed by strangeness and have been observed, and a postulated subset of processes that are forbidden by strangeness and provide as test of this theory. I'll get to those in a moment. But I first want to call out a distinctive feature of the resulting theory. Its essence is that the relative parities determined by the specified set of processes accounts not only for the equality of the domains of validity of associated production and parity conservation, it also provides an account for the pairwise appearance of the new particles. In other words, associated production is explained as a consequence of the theory without introducing an additional quantum number. A single quantum number parity accounts for both phenomena. The experimental test of the theory is provided by processes that violate strangeness. These are some examples. As you can see, the initial and final values of strangeness are unequal. 0 and +4 in this process, 0 and -4 in this process, +1 and -3 in this process. Some of these processes may already have been recorded in existing experimental data, but were missed because the final states and processes with the same initial states as these were analyzed under the assumption of strangeness conservation. Analysis of already recorded data may reveal the states whose presence violates strangeness. A search of existing data for processes such as 4 should not involve excessive resources. It should be about 2 orders of magnitude less costly than the typical particle physics experiment, as it involves 2 orders of magnitude, as it involves no accelerator time and no costly new experimental. What is needed is access to existing data in a program that searches for final states in processes, such as 4. In summary, I propose that the domains of validity of associated production and parity conservation are equal because they are physically identical. A single quantum number parity accounts for both phenomena. Different hadron states with the same electric charge and baryon number are distinguished by measuring different values of parity. The theory developed on the basis of this physical identity determines these relative values in a way of testing the theory that is inexpensive as available. The theory is formulated entirely in terms of symmetry-based dynamics and dependent concepts. It shares this with what is called algebraic quantum field theory. In this approach, the physical system is determined by algebraic relations among the observables rather than by equations of motions of quantum fields. My theory is probably a special case of algebraic quantum field theory. I say probably because algebraic quantum field theory involves an additional concept, the algebraic relations between the observables rather than by equations of motion quantum field theory. These relations remain to be investigated, and that's why I say that it is probably a specific case of algebraic quantum field theory. Thank you.
Thank you, Professor. Thank you very much. We have a lot of time for questions. And Mr. Botala, how would you like to proceed? Should we give people the opportunity to ask questions here? Are there questions on the chat?
We'll give the time here. And I'm very impressed seeing Professor Richard presentation. He has proved age is not a number, it's just a number. So it's very impressed, and I will leave some time here. So if anyone have any questions, please go ahead and ask Professor Richard.
All right, thank you very much.
Let's give people a few minutes. In fact, feel free to ask, unmute yourself and ask a question or post a question on the chat. I'm monitoring both. So, and I wanted to make sure that our next speaker is
I'm sorry, I don't understand the question.
Yeah, I don't know if there's been a question yet. I don't think there has. I haven't heard a question.
So I have a question.
Yes.
And I'm not an expert in some of the things you presented, so some of this might be an ignorant things to ask. But in the context of some of the experiments coming online or recently done with particle accelerators, is there a way, can this, what you're describing, be easily measured? Or is this something that's kind of buried with the experimental limitations that we have right now?
Well, these are the processes that are provided. Can you see my slide?
Yeah, I can see your slides.
Okay, these are processes that violate strangeness. So they provide the experimental test of the theory. And what I'm saying, that these processes may be hidden in the data produced by these collisions. They would not have been found because the analysis of the final states are limited to processes that conserve strangeness. So what has to be done is to look at the data produced by these processes, such as these three, write a program to analyze the final state, searching for these kinds of states. And what I'm saying is that this should not involve any accelerator time and no new instrumentation. Did I address your question?
Yeah, so the public data archives should have this if somebody goes digging for it. Is that a correct summary?
Yes, I'm sure the repositories of data have the results of these collisions. It's just that the analysis of the final states have been limited to processes that conserve strangeness, and these processes all violate strangeness. Does that address your question?
So do you have any students, or are there other people that are looking for this right now?
No, as far as I know, no one is looking for it. To
Thank
my
you.
knowledge. I'm hoping that someone will look for it.